I will now talk about how to count the number of permutations and combinations of elements of a set where we can take the same element from the set more than once. So let's start with permutations with repetition. And the number of k permutations of a set of n objects with repetition allowed is n to the k. So what does this mean? Imagine that you have n objects. Okay, so you have a set of n objects. Let's call them object 1, object 2, all the way to object n. From this set, you want to form a k permutation. Okay, so we have, think about it as a sequence of k elements. These elements need to come from that set of n objects. And this is element 1, element 2, element 3, all the way to element k here. Now, I can take, in each one of these k positions, I can take any of the n elements and put it there. But think about it that when you take the element from there, from the set, and put it in one of those k entries, you also put back that element in the set that you can reuse it again. So for example, if I put O1 in position 1, then the second time I need to choose an element from that set and put it, for example, in position 2, I can still choose O1 again. And then the third time in the third position, I can choose O1 as well, and so on. So if we think about it, this is a simple case actually of application of the product rule. Because here for the first position, I say that I can use any of the n objects, right? So I have n possibilities of putting an object there. For the second one, since I allow repetition, I can choose any of the n objects, so it's n. For the third one, since I am allowed to allow repetition, I can choose any of the n objects, so this will be n, and so on. So this will be n. Using the product rule, it's n times n times n, k times, and this equals to n to the k. Now, here on the side, I want to remind you that if we don't allow repetition, if no repetition, then when I look at this sequence of k elements, 1, 2, all the way to k, for the first position, I can choose any of the n elements. Once I choose that element, imagine it's O sub I. I cannot choose O sub I anymore. This is why for the second position, we will have n minus 1. For the third position, we will have n minus 2 because we cannot choose the elements that we have put in positions 1 and 2 already, and so on, right? So this is the major difference between with and without repetition. With repetition, you can basically in any of the k positions, you can put any of the n elements because you can reuse that element, and this is where the n to the k comes from, okay? And with no repetition, that's where we get the p of n comma k, which is n factorial divided by n minus k factorial. And applications of that are very simple here. So for example, if I want to do how many bit strings of length k are there. So the set of objects really has only 2 objects in it, 0 and 1. And I want to choose a bit string of length k, right? So here for the first position, I can choose any of these 2 elements, 0 or 1. 0 or 1 in the second position, all the way to the kth position where I can choose 0 or 1, so it is 2 to the k. Right? So this is a straightforward application. Here the n is 2 and k is k, of course, in the problem. Another problem here, how many words of length 10? So this is where the k comes from, of length 10. So k is 1, 2, all the way to 10. So k equals 10. How many words of length 10 can be written with the letters A, B, C, D, E, F? So this is the set of objects that we can use. And the n here is 6. Right? So in this case, we have 6. The theorem or the result tells us that the number of possibilities is 6 to the 10. And this really comes from the fact that I can put in the first position any of the 6 letters, in the second position any of the 6 letters, and in the 10th position any of the 6 letters. So you multiply 6 by itself, 10 times 6 to the 10. Okay? So it's a very simple rule. When you allow for repetition, think about it as you take an element from the set, put it in your in your string or in your sequence, and put it back also in the set so that you can use it again. Okay. When it comes to combinations, with repetition, it's a little bit more complicated or more involved here. So now I have a set again, same story. I have a set of n objects, and I want to take a subset of size k. Now I want to take a subset of size k, oi1, oi2, oik, and we want this to be a subset of this. Now these here, these elements, I'm allowing repetition now, okay? So this is not the standard notation of set, because if the set, for example, if the set has 0 and 1, I could choose 0 multiple times, I could choose 1 multiple times here, okay? But I want to look at this set of n elements, and I want to take a subset of k, where that subset can have the same element multiple times. So I can take O1 k times, I can take O2 k times, I can take O1 2 times and O2 k minus 2 times, and so on. Okay, so this is a difference between combinations without repetition. Now, how do we reason about this? It's very important. It's very helpful here to visualize the problem as follows. So now you have these objects. Think about the objects, put them in a line. You have object 1, object 2, object 3, all the way to object n, and object n minus 1 here, right? So these are the n objects. And I want to choose k elements of this with repetition. So I could take k times O1 or k times O2 or whatever, or I can take 1 O1, 2 O2, 3 O3, and so on, such that these numbers add up to k. So one way to reason about it is that if you think about separating these here, so let me put boundaries between these objects, boundaries here that I will draw with lines. So this is 1, 2. I will separate these objects. Since there are n objects, you will see that there are n minus 1 red bars. Okay, so we have n minus 1 red bars. Now I want to take k of this object, where the k can be again co-O1, k instances of O1. So now I will denote by a star the number for every instance of an object. I will put a star in the column for that object to denote that I have taken one instance of that object. So for example, if k, let's say k is 5, and I want to take 2 copies of O1 and 3 copies of O2 and 0 copies of OI for I greater than or equal to 3. Okay, so I will take 2 copies of O1, 3 copies of O2, and no copies of any of the other OIs. This will give me five copies, right? So I will denote this by stars. I will say that I am assigning 2 stars to O1. I'm assigning 3 stars to O2. And then I'm assigning 0 stars here. No stars for any of the others. If you take another assignment or another combination of 5 elements, another combination, for example, is 1 O1, 3 O2, and 1 O3, and 0 everything else. This would be 1 star for O1, 3 stars for O2, and 1 star for O3, and then no stars there. So now if you look at the problem like this, this becomes, now how many stars do we have total? In every row, you have to have k stars, right? So now these stars, you can think about them as, then you can think about the problem as, I can put k stars, here, and I want to separate them by n minus 1 bars. I want to separate them by n minus 1 bars, 1, 2, and so on. Separate them by n minus 1 bars. Then this is analogous to the problem we are interested in. Why? Because once you draw the n minus 1 bars, the number of stars to the left of the first bar, this will be the number of times you took object 1. the number of stars between the first and second bar will be the number of objects you took, the number of times you took object 2. Then between the second and third is the number of times you took object 3, and so on. And then to the right of the rightmost bar, this is the number of times you took instances of object n. And here is object n minus 1. So now the problem becomes, our problem becomes that we have k stars, right? We have k stars plus n minus 1 bars, and we want to k stars and n minus 1 bars, and we want just to choose the places for the k stars or the n minus 1 bars. So in other words, we have an array. Think about it as an array that has positions 1, 2, 3, 4, all the way to n minus 1 plus k. This is how many positions it has. And in these ones, I will put k stars and n minus 1 bars. So the way to look at it, how many places, how many ways I can put n minus 1 bars in an array of n minus 1 plus k, n minus 1 plus k entries. So again, the problem is how many ways are there to place n minus 1 bars in an array of size n minus 1 plus k. Now here it's now without repetition in a sense, right? Because these are n minus 1 bars. I'm telling you exactly the number of bars. So now this is a familiar problem, because the question now is how many ways I have to choose n minus 1 positions in this array, right? So now this becomes, I have an array of size n minus 1 plus k. I need to choose n minus 1 places for the bars there, okay? Or equally, this would be n minus 1 plus k, choosing the places for the k stars. Because if you choose places for the n minus 1 stars, the remaining positions, the remaining k positions will have stars in them. If you choose k stars, the k places for the stars, the n minus 1 remaining positions will have the bars in them, okay? So this is the number of ways you can choose a subset of size k from a set of size n such that repetition is allowed, okay? Again, I repeat, this is the number of ways of choosing a subset of size k from a set of size n when repetition is allowed. And here, in this case, the number of objects in the set is n. The number of objects, like if you are working with binary vectors or binary strings, then the set will have the two elements 0 and 1. And then you may ask about giving us combinations of k elements from that set with repetition, okay? So this is the formula here. And always when you think about this, think about the analogy. What are the stars? What are the bars here when you are trying to solve a problem, okay? So let's see an example. Here is an example of the use of this theorem. And how many solutions are there to equation x1 plus x2 plus x3 plus x4 equals 15? Okay, where x1, x2, x3, and x4 are non-negative integers. So the way we think about this here is that think about it as the number of objects that you have, the set of objects you have are the x1 objects, the x2 object, the x3 object, and the x4 object. From this, you want to take a 15 combination from this, okay? So you want to get a 15 combination of this with, we want to get from this a 15 combination where we are allowed a repetition. So I can take x1 5 times, I can take x2 5 times, I can take x3 5 times, x4 0 times. Then I have actually gotten a solution to that equation. So if you think about it, and I put 15 stars, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If you look at the solution to this problem, is that I need to assign these stars to x1, x2, x3, x4, such that we have 15. So I can put on the line 15 stars. And now my job is to put 3 bars here, 3 bars, so that I can get solution to this problem. So for example, I can put a bar here, I can put a bar here, and I can put a bar here. If I put these 3 bars here, then I'm saying x1 equals 3, x2 equals 4, x5 equals 2, 4, 6, and sorry, not x5 here, x3, and x4 equals 2. Okay, so you see how putting 15 stars there, drawing 3 bars to separate them, I already got a solution to that equation. Another way, for example, is that I can draw the bars here. I'm going to use now the blue ones. I can draw a bar here. I can draw a bar here. I can draw a bar here. So here, what am I saying is that to the left of the first bar is the x1, the instances of x1. So x1 is 0. Between the first and the second, this is the x2. And we have 2, 4, 6 stars. Between the second and the third, this is the number of stars we are assigning to x3, which is 9. And after, to the right of the rightmost bar, this is the number of stars we assign to x4. So if we now, this assignment of bars, this placement of bars correspond to the solution that x1 is 0, x2 is 6, x3 is 9, x4 is 0. And you can repeat. Now you can draw bars, 3 bars anywhere, and you get any way you place the 3 bars, you will get a solution. So in particular, for example, I can put the 3 bars, all of them on the left. So I can put the 3 bars here, 1, 2, 3. So this, what does this correspond to? This corresponds to x1 being 0, because to the left of the leftmost bar there are no stars. x1 is 0, because between the first and second there are no stars. x2 is 0, because between the second and third bar there are no stars. x3 is all 15 stars. x1, x2, x3, x4, sorry about that. Okay, so we have, this is a possibility. You can put, of course, all the 3 bars on the right, all the way on the right, in which case x1 is 15 and the other 3 variables are all 0. So if we think about the problem like this, now we have a problem of combinations with repetition, where we have the number of bars, we have the n objects, n is 4, so the number of bars is 3, and we want to get the k combinations here, k combinations, where k is 15. And by the result that we just saw on the previous slide, the number here is, you can take the 15 stars plus the 3 bars, which is n minus 1, and you choose which one of them you want to take. You can either choose the 3 bars, or you can choose the 15 stars to place them. Either one of them is going to be the same, it will give you the same quantity. So these two are equal here. Okay, so this is how we reason about combinations with repetition.